Hello, this is Lynn McGuire. I'm a senior principal consultant and lead for energy transition, air quality, and carbon management solutions at Geosyntec Consultants, based out of the San Francisco Bay Area in California. I'm very honored to be presenting the work of our full-length technical paper prepared by myself and co-authors Barb Neary and Hong Jin of Geosyntec. We are a consulting and engineering firm and an exhibitor sponsor of the AWMA ACE 2020 conference. This presentation, Options for Industrial Businesses Towards Achieving Carbon Reduction Targets, brings together trends and information from our experience working with industrial businesses in this space. This presentation is a high-level overview. We will touch on what some of the drivers are for setting carbon reduction goals. We will explain the importance of carbon emission counting for Scope 1, 2, and 3 greenhouse gas emissions. We will discuss some important considerations in developing a greenhouse gas emission reduction strategy and cover some of the most effective types of carbon reduction opportunities, including energy efficiency improvements, renewable energy, fuel switching, use and procurement of materials, carbon capture and storage, and investment in carbon sequestration or natural resource solutions. Throughout this presentation will be examples of how these approaches present both risks and opportunities to businesses that are energy consumers and producers. We are experiencing an unprecedented time of change. Extreme weather events like the wildfires and electricity interruptions in my neighborhood, coping with existential threats as we are with COVID-19. It is giving us a unique look at the impacts of our business as usual on society and environment. These events have caused businesses and us personally to consider how we conduct our daily activities to minimize impacts and become more resilient. Though a global and political issue, many of the policies related to climate change in the U.S. are adopted at the local city, county, and state level. In response, our energy transition is posing business risk, but also opportunity and innovation. Each business is on a journey and navigating this as best they can. However, investors like Vanguard, BlackRock, and State Street, and shareholders aware of the challenges have demanded more transparency around climate risks, both around the changes happening around prevention, the transition risks, and the changes to adapt to the consequences, physical risks. The TCFD is a global group charged to develop a voluntary framework that businesses could follow in disclosing their climate-related risks. Their financial recommendations were reported in June of 2017, and by last year, over 1,100 companies have used the framework, comprising 78% of the world's largest companies. As businesses disclose the transition risks, many are setting targets and goals, tracking metrics deriving from Scope 1, 2, and 3 greenhouse gas emissions, energy, and fuel use, and considering carbon reduction strategies, often as part of corporate sustainability ESG planning to manage the risk, improve the carbon footprint, and capitalize on opportunities. In the U.S., the three largest contributors to the overall greenhouse gas inventory are the transportation sector at 29%, the generation of electricity at 28%, and the industrial sector at 22%. Industry plays a key role as it also influences the transportation and electricity sectors indirectly as a consumer. The challenges for industrial businesses are many. Some that are the drivers for carbon reduction efforts include sustainability program goals, low carbon regulations and mandates from local jurisdictions, supply chain mandates from those you sell your products to, cost savings and investment, incentive programs, scheduling of asset retirements, prioritization of continuous improvements, reputation and market, and risk reduction. To develop a carbon strategy, businesses must at a minimum have a clear picture of their current carbon emissions, including where they are located, how they define operational boundaries, and what their most significant emission sources are. Companies will generally report their direct Scope 1 emissions, which are those from sources owned or controlled by the company, including process or combustion emissions from boilers, engines, or vehicles, and their indirect Scope 2 emissions from the company's consumption of purchased electricity, heat, steam, or cooling, following the principles in the Greenhouse Gas Protocol. Some companies choose to include Scope 3 emissions in their corporate inventories. Scope 3 emissions are other emissions generally outside the company's control that occur within their supply chain and provide a more complete picture of a carbon footprint. Whether to account for Scope 3 emissions depends on supply chain relationships, availability of reliable data, and degree of responsibility or influence desired. A company's carbon reduction strategy and targets are informed and influenced by the greenhouse gas inventory aligned with their sustainability program goals and the policies of the country and local jurisdictions they operate in. They also benchmark themselves against competitors, suppliers, and customers. Companies can also elect to set science-based targets, SBTs, that are aligned with the level of decarbonization required to keep global temperature increase to below 2 degrees Celsius compared to pre-industrial temperatures. An example given in the Greenhouse Gas Protocol, Procter & Gamble Company set a very near-term SBT for 2020 to achieve 30% reductions in greenhouse gas from the 2010 base year and included other sustainability measures across its value chain. Some companies have chosen a goal of achieving carbon neutrality or net zero carbon emissions by a certain year. You can appreciate the challenge this presents in balancing the scope 1, 2, and 3 emissions to a net zero and the degree of influence on energy providers and material suppliers and the resources a company must have in order to achieve it. The rest of this presentation will cover the types of carbon reduction options with examples. The most obvious and most cost-effective means to decarbonize industrial operations is to find ways to do more with less fuel, Scope 1, and electricity, Scope 2. Energy efficiency has potential to reduce both. Because energy efficiency is not a new concept, it is perhaps not as exciting or capable of drawing attention as other strategies. In the U.S., energy efficiency solutions alone are credited with the potential to account for as much as 50% of greenhouse gas reductions to meet climate goals. That's why we're discussing this alternative first. With changing energy pricing and innovations, cost savings options can result from taking a second look at past ideas that were maybe not economic enough to justify at the time. Also, in circumstances where energy is cheap, like low-cost natural gas, being more efficient may not be a priority until you factor what it can do to your carbon footprint. Easier said than done, though. Many companies maintain a list of good energy efficiency projects that await the right timing and budget cycle to be executed. Planning and scheduling these projects is often done incrementally. Incentives and access to capital really help here. One way to visualize the attractiveness of energy efficiency projects in creating a greenhouse gas reduction strategy is to create marginal abatement cost curve, or MAC, of projects identified through surveying experts familiar with the facility or by conducting an energy audit. In a MAC curve, each bar represents a different opportunity to reduce emissions. The width of each bar represents an annual emission reduction potential compared to business as usual, and the height represents the average net cost of reducing 1 ton of carbon dioxide equivalent through that activity each year, including annualized capital costs. The opportunities below the horizontal axis are cost saving. Opportunities above the horizontal axis reduce carbon but have a net cost. This is an example adapted from the California Air Resources Board during rulemaking for its cap and trade program and depicts energy efficiency options for a typical oil refinery. Optimizing and maintaining heat and steam systems are some of the cost-saving greenhouse gas reduction opportunities, while replacing boilers and heaters require big investment. Energy efficiency measures also include programmatic approaches, such as implementing or boosting engagement in a voluntary energy management program to align with your carbon reduction goals. We provide references and links to 3 programs that many companies are already participating in. Energy Star is the US EPA's program around since 1992 that we associate with appliances and was expanded to industrial energy efficiency in the year 2000 and provides many tools, energy guides, benchmarking, best practices, tracking performance, engagement, and communication, as well as recognition awards. The ISO 5001 Energy Management Standard Framework, developed in 2011, is based on the classic Plan, Do, Check, Act process of continual improvement. It starts with an energy policy, fixing targets, gathering data, measuring results, reviewing effectiveness, and continually improving. The recently developed guidelines for integrated energy management strategy, developed by the World Business Council for Sustainable Development, wisely applies the nexus of energy management with sustainability goals. Powering facilities with renewable electricity is another way to achieve significant reductions in reported Scope 2 greenhouse gas emissions. Facilities can install their own self-generated rooftop solar PV panels or ground solar array or small wind turbines behind the meter with the utility to reduce energy demand and the associated greenhouse gas emissions. Companies also contract for off-site generated renewable sources by purchasing not only the power, but also renewable energy certificate or credit, called RECs. Physical power purchase agreements, or PPAs, have been the most common form of renewable energy transaction. They are contracts for renewable power where the corporate buyer is purchasing the electricity generated for their facility and the RECs at a certain renewable energy project. Virtual PPAs have become fastest growing transaction structure today for corporate buyers because the buyer does not own and is not responsible for the physical electrons generated by the project, but does still receive the RECs. Instead of routing renewable power directly to the buyer's facility, the generation facility sells their renewable power directly to the grid. The most common types are wind or solar contracts with and without battery storage. Our full paper describes a few examples recently reported by others of green power action by corporate buyers. I'll share headlines from one, an example from the power generation industry, highlighting the rapidly changing competitive costing of renewables plus storage. Xcel Energy has a goal to reduce carbon emissions by 60% by 2030, replacing coal-fired capacity with low-carbon renewables. Xcel recently received proposals for natural gas and wind or solar plus storage at unprecedented low costs. The median price bid for wind plus storage projects was $21 per megawatt hour, and the median bid for solar plus storage was $36 per megawatt hour, representing a 20% drop in cost over pricing from just 1 year ago. Now we'll switch gears and discuss fuel switching options. Substitution of carbon-intensive fuels in manufacturing processes can be quite difficult, especially to meet high thermal energy process needs. Many large manufacturers and industrial sector collaboratives of steel, cement, chemicals, petroleum, and petrochemicals are weighing options because fuel switching can result in significant greenhouse gas reductions when moving to even incrementally less carbon-intensive options. It is important, however, to realize that every fuel has its own carbon footprint, including not only the carbon released when it is burned, the red part of these bars, but the carbon that it took to produce and transport the fuel. Thus, low carbon and conventional fuels are often characterized through a life cycle assessment to determine unique carbon intensity. The figure shows a comparison of carbon intensities in grams of carbon dioxide equivalent per megajoule for conventional fuels. You can see the general advantage of moving from coke or coal to LPG or natural gas. This is another carbon intensity example of how not all natural gas is created equal, considering its origin and life cycle. Again, it is important to understand the carbon intensity value for the fuel, including all processing and shipping components, to make clear choices that benefit greenhouse gas reduction decisions. This example compares shipments to the European market of US-produced LNG compared to LNG from Algeria or natural gas from Russia to substitute for European regional coal. Depending on the origin of the natural gas, how it was extracted, compressed, and transported, the greenhouse gas emissions are quite different. The carbon intensity of U.S. shipments compare favorably, while one source of natural gas from Russia is almost as carbon intensive as the coal it would replace. There are, of course, alternative non-fossil based fuels to consider. Biomass is organic material from plants and animals that is considered a renewable source of energy. Plants store energy in biomass through photosynthesis. Burning biomass releases the energy as heat. Though ethanol is considered a low-carbon fuel blended with gasoline in the U.S. to lower the carbon intensity of gasoline, not all ethanol is created equal. This is an example of how using biomass as a fuel in ethanol production can create a very low-carbon ethanol biofuel. Almost half of the life cycle energy contribution for Brazilian sugarcane ethanol is in the ethanol production step, which uses heat energy. By supplying the production heat energy using a renewable biomass fuel, the waste bagasse from the sugarcane itself, the production step contributes almost no greenhouse gas emissions to the overall carbon intensity, cutting the fuel carbon footprint in half. There are many renewable fuel options for deep decarbonization. Biomass and renewable biogas are commonly waste-derived fuels, the feedstock of the future, but cost and volume availability, substitution feasibility, and distribution hurdles make use of biofuel and biogas limited currently. Hydrogen is another fuel that is receiving attention, but not all hydrogen is created equal either. Conventional hydrogen produced by steam methane reforming unfortunately generates very large quantities of CO2 as a byproduct and is becoming known as gray hydrogen. Projects are proposed to capture CO2 from hydrogen manufacture and sequester it, resulting in what is known as blue hydrogen, which is less carbon intensive. By contrast, renewable green hydrogen is produced in much lower quantities by electrolysis of water, a very energy-intensive process that can be powered by excess intermittent renewable wind or solar as a form of energy storage for later use called power to gas. Use of renewable natural gas or hydrogen with conventional natural gas to generate power can be a good load-following complement to intermittent wind and solar generation to decarbonize the grid. This may pave the way for electrification of industrial processes using green power, but the electricity supply must be affordable and reliable. Cement manufacturing is an example of a complex carbon reduction issue requiring consideration of multiple approaches. Since cement manufacturing alone is reported to account for about 7% of all global carbon emissions and is essential in infrastructure and buildings, international collaborative efforts are underway to develop decarbonization solutions that maintain product integrity. Everything from energy efficiency to using alternative fuels to carbon capture to new formulations are being attempted. Manufacturing cement requires high temperatures too, which require large amounts of fuel, but it is the decomposition of limestone in the formation of clinker that generates at least half or more of the CO2 emissions of cement manufacturing. Thus, cement manufacturers are attempting to procure lower carbon or recycled materials to replace some or all of the clinker and researching alternative binding materials to directly reduce the plant's Scope 1 greenhouse gas emissions and the product's carbon intensity. Carbon capture projects resulting in negative emissions are key strategies to hasten meeting decarbonization goals and support carbon neutrality plans. Preventing leaks of methane, which has a high global warming potential 25 times higher than CO2 through toughening regulatory standards, is a form of capturing carbon. However, there are still industrial waste and biogenic sources of methane that are large contributors to greenhouse gas emissions on a regional and global scale. This map shows Southern and Central California sources of methane found in a recent measurement study conducted by NASA's Jet Propulsion Laboratory that flew over the state of California with remote sensing infrared imaging equipment. Blue dots are waste sources, landfills, contributor of 41% of California's methane emissions. Green dots are agricultural biogenic sources at 26%, and yellow blocks are energy sites of oil and gas production at 26% as well. Collection of methane from landfills or anaerobic digesters are examples of carbon-negative approaches that can also be renewable energy feedstock if it's captured and used. Also, collection of CO2, not only from industrial stacks, but also by commercializing direct air capture DAC systems. Big fans that capture ambient air and filter and separate CO2 from the air result in negative emissions and might produce CO2 for use in beverage production as an additive in cement manufacture or in novel syngas production, or simply sequestered. Carbon capture and sequestration, CCS, is now recognized as a necessary strategy to meet the goals of the Paris Climate Agreement. CO2 has been injected into geologic formations since the 1970s in the U.S. for enhanced oil recovery to extend the production life of oil fields and incidentally store CO2. It was only economical because the significant cost of capturing, processing, compressing, transporting, and storing CO2 is offset by the value of the incrementally produced oil. Incentives and programs such as the 45Q tax credit in California's LCFS and cap and trade programs are now establishing incentives and accounting systems and providing reward for the climate benefits of CCS. Reservoir characteristics, location, pipeline infrastructure, funding, collateral impacts, long-term monitoring, risk management, and many other factors must align for implementation of CCS to be economical and successful. An example of large-scale CCS for enhanced oil recovery is a project being developed for California Resources Corporation, Elk Hills oil field, the first in California. When completed, the project will capture and geologically store 1.5 million metric tons of CO2 emissions from the nearby Elk Hills power plant. The business community is investing in solutions and programs aimed at natural processes and land use management that maintain vegetation, trees, soil, and wetlands to sequester carbon. Some of these nature-based solutions are more economical on a dollar per ton of carbon basis than man-made sequestration methods and have attractive co-benefits to air and water quality, ecosystems, soil health, resilience to climate change, and wildfire prevention. European oil and gas companies are leading the way. Last year, a major Italian energy company announced plans to offset carbon by developing and funding large forestry projects in Africa through the UNFCCC REDD+ program. Soil carbon management and sequestration to prevent depletion of soil organic carbon is getting attention as well. Some report that the Earth's soils contain more than 3 times more carbon than is stored in the atmosphere and 4 times more than the amount in all living plants and animals. But soil carbon sequestration programs are still in the research stage, and protocols for accounting are in the pilot stage. While this strategy may have enormous potential and co-benefits, some of the challenges for business participation are in quantifying reductions, accounting for effectiveness over time, demonstrating the permanence of the reductions, and uncertainties such as resilience to weather events. To summarize, there are recent drivers that promote setting carbon reduction targets. We covered the key role of energy efficiency, the lowering costs of renewable electricity, the options for low carbon fuels, and consideration of carbon intensity, the challenges of feasibility, availability, reliability, and affordability of carbon reduction options, that carbon capture and sequestration is getting attention and incentives, and that businesses are investing in natural carbon sequestration. I would like to acknowledge the 2 co-authors, Barb Neary and Hong Jin. Please look for the full technical paper on this session and feel free to contact us with questions.